Welcome to your tutorial on data cleaning. We'll start by looking at identifying impossible values and response sets. Okay, so we have a data set here with a number of variables. We have ID, gender, which is a categorical variable. We have favorite color, which is also a categorical variable. We have happiness and vitality, which are interval level variables measured on 1 to 10 scales. And then we have reaction time, which is a ratio level variable that goes from 0 to infinity. So the first thing we're going to do is look for impossible or out of range values. So the easiest way to do that is actually just through the descriptive statistics and use the frequency distributions. So if we click here, and what we'll do is just get the frequency tables for all of the variables except for ID, ID. So we click OK. And what we get here are different tables, and it tells us which values we have. So we have our 5 variables, and then if we go down, for gender, we have male and female, and then we have this random 4 here, which doesn't make sense because we don't have a category for 4. If we look at favorite color, okay, we have red, blue, green, yellow, everything's good. Happiness, we see that we have scores of 4, 5, 6, and 7 on 10, everything's fine. And same with happiness and vitality. And then we look down here, everything is within normal range as well for reaction time. So we do have an impossible value here for gender. And essentially what that means is we have to go deal with it. So since it's a categorical variable, it's a categorical and demographic variable, so unless we can be really certain about what this should have been, so if we can access the original data and see what the participant entered at first, then we have to get rid of it. So if we go back to our data set, we have, we can see here, because the data set's not very big, that the 4 is right there. So what we really should do is delete it. However, when you are deleting something like this, it's not a bad idea to check and see what else that participant has answered. And we notice here that we might have evidence of a response set, since this participant appears to have entered the score 4 for every variable, even if that doesn't make sense like it does here. So I would say in this case, based on the 4 here and the fact that there's 4s everywhere, this would be a worthwhile candidate for deleting them. So what we're actually going to do is we're not just going to delete the score here, we're going to take out this whole row. So we can delete participant 13 entirely. Actually, I don't know what happened with our numbers, but anyway, so we can delete that here, and that participant is gone. So we have dealt with our impossible value and our response set at the same time. If there had been any other impossible values in any of the other variables, you would just need to delete it if you're not sure what it should have been. Next, we'll look at handling missing data. Okay, so next we need to deal with our missing values. So if we run the frequency tables again, we can actually get a sense of how much missing data we have, and it actually tells us here right in this row right here. So for gender, we have 1 missing score. For favorite color, we have 6 missing scores. Happiness, we have 1, and then vitality and reaction time, we have none. So if you recall, how we handle missing data depends on the variable. So when it comes to categorical variables, we simply need to remove the variable and code it as missing, or remove the data and just code it as missing. For categorical variables that aren't demographic, if we have more than 5% of the data as missing, we can create a new category and call it other, or we can just leave it as missing. And then for interval and ratio data, so these 3 variables here, we would replace the missing variable with the mean. So we'll go through each of those right now. So if we look here, we can see what the overall percentage is. So on gender, 1% is about 3. However, we do see here that on favorite color, 6 missing scores is actually equivalent to about 21%. So this means that for this variable, we could recode those missing scores as an other category. And then since this is an interval or ratio variable, we would replace this with the average score for all of these. So let's go do that. Okay, so for gender, we need to replace the missing score with a code. So we'll give it a 99, and then we really need to go back to the other side here and make sure we know that, or SPSS knows that that 999 or 99 means it's missing. Okay, if we go back to favorite color, so we have 4 categories and we have a lot of missing data here. So what we're going to do is create a 5th category and call it other. Okay, so we have 5. And then here, and then we have to go tell SPSS that those are another category. So we click here, we would add 5 and call it other. Okay. And then finally, for the happiness variable, we can see that we have the missing score right here for participant number 24. However, we do need to figure out what the average of this variable is in order to plug in that score. So what we're going to do is do analyze descriptives. We can stay at frequencies or go to descriptives. Either one will give us the option. So we'll take out all the variables that we're not interested in, and we will simply ask SPSS to generate the mean score for this variable. We click OK. And what we see here is that the mean score for happiness is 5.5. So what that means is that we can go and recode this missing variable with the score 5.5. So here it is. Excellent. So now if we rerun our descriptive statistics with all of our variables and look at our frequency tables, we'll see that the corrections have been made. So you will notice that the only remaining missing score is on gender, and that makes sense because we can't impute that. However, for happiness, we no longer have a missing score, and you do notice that we have one observation of 5.5. That's that new one. But the average hasn't changed because we simply replaced an extra score that was blank with the average, so it's not going to have an impact on the average. And then gender now, it tells us the code has been properly associated with the missing variable. And then we have our other category here. So that is how you would handle your missing data in SPSS. Now we'll look at identifying and managing univariate outliers. Okay, so the next thing we need to deal with are our outlier scores. So if you recall, outlier scores can only occur on interval or ratio data, and it's when we have an observation that's significantly different than the rest. So in SPSS, we're going to focus today on finding any outlier scores on this reaction time variable. So what we're looking for are scores that are very different. And if you recall, we do that by calculating the z-scores to identify which ones are a problem. So to get the z-scores for all of these observations, what we're going to do is do analyze, descriptives, and then descriptives. We're only going to select reaction time, and we're going to check this little box here, save standardized values as variables. So this is what it's going to do is create a new column right here, a new variable with reaction time and a little z in front of it, and that's going to represent the standardized scores of all of these scores. So we click OK, and we can close that. And what we have are all the z-scores. So if you recall, we're looking for scores that are bigger than 1.96 or smaller than negative 1.96. So these are all fine. They're within 1 point of the mean or of the center. So very normal scores. So if we go down, everything's fine until we get here. We notice we have a score of 4.68. Obviously, I made this a really big outlier, so it'd be easy to find. But this score is much bigger than 1.96. So if you recall, we need to handle this by doing something called Windsorizing, where we would replace this score of 15 seconds with the score that is the most extreme but still within normal range. So if you remember, the formula for determining that would be 1.95, which is just one value inside of 1.96, times the standard deviation of this variable plus the mean of this variable. So to get that, the first thing we need to do is calculate the mean and standard deviation for this variable here. So we do Analyze Descriptives. We'll unselect this box, and automatically, just by being in the Descriptive Statistics options, we're going to get our mean and standard deviation right here. So we can click OK. And we have a mean of 2.93 and a standard deviation of 2.58. So we'll grab the calculator here. And so the formula is going to be 1.95 times 2.58 plus the mean. So we'll do that here. 1.95 times 2.58 plus 2.93. And that gives us 7.96. So we're going to close this and replace this score of 15 with a score of 7.96. And what that represents is the score that is the most extreme but still within normal range. So if we were to rerun this, this would now be equivalent to about 1.95. Now, unfortunately, if you do rerun it, it's going to readjust now that you don't have that outlier score in it. And it's still probably going to show this as an outlier, but you only want to do this once because it's going to keep readjusting the distribution. So doing this one time is sufficient. And that's how you do perform Windsorizing. Finally, we'll look at measuring univariate normality. Okay, so the last thing we need to look at is the univariate normality for our variables. So what we're going to look at is happiness and vitality, and what we're interested in determining is whether either of those variables are significantly skewed or have significant kurtosis. So to calculate this, it's actually pretty straightforward. Again, we go to Analyze Descriptives, and we can do this from frequencies or descriptives, but either way. So we'll take out that one, put happiness and vitality here, and then in options, we just need to select the distribution options under and select kurtosis and skewness, and this will automatically have SPSS generate the kurtosis score as well as the standard error of kurtosis and the skewness score as well as the standard error of skewness. So we click OK and run the analysis, and we have our window right here. And basically, we have all the same descriptive statistics we had already asked, plus we now also have this information on skewness and kurtosis. So what we need to do is divide the statistic by the standard error to obtain the ratio. And if we recall, we're looking for values that are bigger than positive or negative 1.96 to indicate that we have an issue. So if we use, for example, the happiness variable, if we look at skewness, we have 0 divided by, it's not going to let us do this, but, or will let us, but anyway, we'll do 0 divided by 0.434, and we get 0 naturally. Okay, so it means we have no issues with normality or the skew on this variable. It means that it's rather has a nice distribution, kind of like this. Kurtosis will do the same thing. So we have negative 1.12 divided by 0.845. And this time we have negative 1.33. So even though this is bigger than 0, or smaller than 0 rather, it's not smaller than negative 1.96. So we don't have a significant problem here. There's a slight issue with the pointiness or flatness, however, not enough that we need to worry. Okay, next we'll look at vitality skewness. So we have 0.164 divided by 0.434. And this time again, we're much smaller than 1.96, so we don't have any issues with the skew on this variable as well. And then let's do the kurtosis one. So we've got negative 1.043 divided by 0.845. And this time again, although we're bigger than 1, smaller than 1, we're not smaller than negative 1.96. So we can conclude that there is no significant issue with kurtosis either. Okay, so that covers everything that you should need to prepare your data set for analysis. And that is that. So if you'd like, I can quickly show you what would happen if we had some issues with skew. But let's see here, I'll replace. Okay, so I've just replaced this variable here with a lot of very extreme scores. So if we run the descriptives on just the regular reaction time variable, this time we have, so you see here the value is changed a lot. So now we have, for skewness, 1.209 divided by 0.434, and we have 2.79. So this is bigger than 1.96. So we would say in this case, since it's a positive value, that we have a significant positive skew on that variable. Okay, so it is significantly positively skewed, so we would have to report that. Kurtosis, I think, is still fine, but we can check it anyway. And yeah, so much smaller than 1.96. Okay, so that is everything you need, and there we go. So thank you.